restrictions like 15,000 nodes and elements. All right, so let's go ahead and go to ANSYS 2023 R1. There's a ton of applications here. But if you scroll down here, you'll see mechanical APDL product launcher. That's the icon we want to click on. So make sure you click on the product launcher, not this the APDL one, the product launcher. So go ahead and click that. And then the first thing we need to do is set up a working directory. So this working directory should be unique for every assignment. The reason why we do this is because if we ever crash ANSYS, we need to be able to navigate to this working directory in the Explorer, Windows Explorer. And we need to find the log file so that we can recover your simulation. If you don't create a unique working directory, it's hard to find this log file, and then it becomes hard to recover your simulation. So a good habit is always to create a unique working directory when you come into here. So you can use the browse option. Typically where I like to put my files is on my documents. You can see I created a folder here for 456L section 1. I'm going to create a new one for MAE 456L section 2. All right. I'll double click into that folder. I'll click select folder, and then you can actually create folders by appending to this working directory in the command prompt here. So I'll append \assignment 1 to that. And then the job name, this assignment 1, is going to be the prefix to all the files it creates inside of this working directory. So once you have these two set up, go ahead and click Run. It'll prompt you if you appended that assignment 1 to the end of this file. It says the directory you selected and the above reference does not exist. Do you want to create it? Click Yes. Just wait here until it launches. In the meantime, if you're curious, you can go look at, using the Explorer, My Documents, look inside that folder. And here you go. So you're just starting the software. This is how many files are created. 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15, 16, 17, 18 files. So by the time we get to assignment 10 in the course, you know, if you don't create a unique working directory, you could have 180 files inside of here. And if you don't change that job name, it appends all these files. It'll append the log files. It's a real mess to try to recover. So get in the habit of making the unique working directory each lab. All right, so this is APDL. This is their kind of their original software, ANSYS. It's built on top of the command line prompt. If you notice, there was two windows launched. One is this output window, and the other is the GUI. The output window is what the original command line prompt used to run in. Basically, somebody just constructed a nice interface here that runs the command line prompts. One thing you'll notice is that if you look at this output window, the X is grayed out. If we ever somehow close this output window, it'll close, it'll basically crash ANSYS entirely. So we always got to keep this output window running in the background. One thing it is useful for is if you ever get a no solution, you can look back on this output window and it will give you some details of what potentially is wrong. So just keep that in mind. Okay, so this is APDL. It's been around, this GUI's been around maybe 30 years now. And if you talk to the ANSYS guys, they basically say most people out in industry are only running this if they have old workflows. So somebody maybe 20 years ago, 10 years ago, set up a script that generates geometry and automatically runs APDL. They'll run the software still. But most of the analysis is being done in Workbench and the newspree software Discovery. And again, Workbench we'll get to here in a couple weeks is basically set up for importing solid geometries. So geometries you build in SolidWorks, Fusion 360, Siemens NX, you can export those geometries and import them into Workbench. So, but this software allows us to do some very simple things like a rigid plate spring system, and allows us to understand, the finite element approach from very simple elements. When we get into Workbench, right, well, it's mainly the brick element, which is an 8-noded, or actually uses a 20-noded element, which has mid-nodes on the side of the element. So it's a very high order. It's a high order element, and we'll get into those details as we go. But we're going to start simple in this class and work up to that. So the menu system here on the left-hand side is basically where we're going to be clicking through. If you click the plus next to preprocessor, you'll notice it expands out. If you click the plus next to element type, it also expands out. So if you go to the how-to, that's basically what the greater than sign there is doing. It's going down a menu, down a menu. We're going to first start by defining the element type. So telling the software what element type we want to conduct the simulation. You have to have some knowledge of what you want to simulate in order to select the correct element type. So we're doing a rigid plate spring system. So the element type we're going to select is this combination element number 14. One thing that'll help you select the correct element is if you go to the help menu. We'll look at that in a second. Okay, so let's execute the first command. So we're going to go to preprocessor element type. So preprocessor element type, and then click add, edit, delete here. You'll get this window here. It says defined element types. There's none defined. So click add. And then here's the library of element types. So if you scroll down on here, these are all the possible element types that you can use to simulate a system. They are grouped together a little bit. This first grouping, structural mass, you'll see link, beam, pipe, solid, and shell. So the link is going to be, we'll get to this element next slab. Is this a 1D element? That's only a 2-force member. The beam is a 1D member that can, that's not a 2-force member. It has a shear force on it and a uniaxial force on it. The solid element is for solid structures, so 3-dimensional structures that we want to mesh, and then shells are for very thin sheets that we want to simulate. If you scroll down below this, they got contact elements, gasket elements, cohesive elements, and then you'll see combination element there where we're going to be, and then below that is thermal mass. So if you want to do a heat transfer problem, you'll see link, solid, and shell. Again, link would be a 1-dimensional heat transfer problem. A solid thermal mass element would be a 3-dimensional heat transfer simulation or element, and the shell would be a thin sheet that you want to simulate the heat transfer in. All right, so we'll hit a couple of these elements as we go along here, but let's start with the combination element. So click combination on this menu here, and then on the right-hand side, you'll see spring dampener 14. This number at the end is element number. Each element has a unique element number. So click spring dampener 14, click OK to select it. You should see defined element types to be type 1 is defined as the combination 14 element. Click close on that menu. All right, and then go up top here where you see the command prompt and type help, HELP, comma, the element number. So 14 in our case is the element number. And click enter. So this command prompt is a way to interact with the output window, basically. But when we type that command in, it brings up the help, and we can read a little bit about this element that we're using to simulate these rigid plates and springs. So combine 14 is a longitudinal or torsional capability. Has longitudinal or torsional capability in 1D, 2D, and 3D applications. So we're going to do a 1D application today. It's just moving the X direction, but we could have the plates moving X, Y, which would be a 2D application, or X, Y, Z, that's a 3D application. The longitudinal spring dampener option is a uniaxial tension compression element with up to 3 degrees of freedom at each node. So those degrees of freedom are translation in the nodal X, Y, and Z directions. So these nodes, if you look at the illustration of the element, each one of these nodes can move in the X, Y, or Z direction. No bending or torsion is considered. So there's no bending to this element. I think like a two-force member almost. And then there's no torsion. However, the torsional spring dampener option can be used where it's purely a rotational element with 3 degrees of freedom at each node, which end up being rotational X, Y, and Z. So if you're maybe simulating a shaft in a car or something like that, and you knew the spring constant of the shaft, you want to look how much angle twist of that shaft, you could use this element, but it's not going to move in the translation directions. It's only going to move in the rotation. So all right. Yeah, the torsional spring dampener is purely a rotational element with 3 degrees of freedom. Right? So it's purely rotational if you use it as a torsion element. It's purely translational if you use it as a longitudinal element. The spring dampener element has no mass, so there's no mass associated with these plates. The masses, however, can be added using the appropriate mass element. So there's a separate element, this mass 21, that we can add to each of the nodes in order to add mass to the rigid plates. All right. If you scroll down through this help menu, there's like input information, output information. But one other thing that's good to look at are the assumptions and restrictions. We don't need to read through all of these, but they do give some useful information. Right, the longitudinal spring element stiffness acts only along its length. Right, so that's like a two-force member it's telling you. The element allows only a uniform stress in the spring. Okay, so just acting like a theoretical perfect spring, not a nonlinear spring, a linear spring. What else? The preload may not change after the first load steps. Preload is ignored in modal and harmonic analyses. Right, so here's another one, good one. So the spring or dampening capabilities, right? So we can also add some dampening to this element. May be deleted from the element by setting the spring constant K or dampening coefficient CV1 and CV2 equal to 0 respectively. So if we don't want dampening, which we're not going to add dampening to our system, we're going to set CV1 and CV2 equal to 0. All right. So let's go back to the software and go on the next step here. We're now going to define 4 real constants that represent the K values, the spring constant values, K1, K2, K3, and K4. So we're going to go to real constants, add, we're going to select the element type and specify the spring constant K1 first. K1 has a value of 250. All All right, so it said go to preprocessor, real constants, and we'll click on add, edit, delete. Pulls up this window, says defined real constant sets. There's currently none defined, so click add. It'll ask you to choose an element type. So when we have one element type, it's combination element 14. So click OK. Then here we go. So here's our spring constant, K value, our damping coefficient, our nonlinear damping coefficient, our initial length, and our initial force. So all we're going to specify is the K value. We're going to leave the rest of them blank. They'll default to their default value, which is going to be 0. But let's start with K1, which we said was 250 Newton meters. So one thing in APDL, we do not specify the units inside of there. We just give it the value, which means we have to keep the units consistent offline. So by specifying 250, our unit of force is now in Newton. We need to keep this consistent throughout the simulation. And our unit of length is going to be a meter. Okay, so when I draw the next node over, I draw these nodes and I say they're 1 kilometer apart, I need to convert that 1 kilometer to a meter, which will effectively be 1,000 meters between nodes. And then when I specify the forces on the nodes, I need to convert this kilonewton to a newton. One other thing I want to show you is if you click off of that, just off to the side, you'll notice you lose that window. And everything's grayed out. There's a button right here that's a stack, like a blue stack on a yellow sheet. If you click on that, it's called Raise Hidden. It'll bring that window back on top. So if you ever lose a window for some reason, you can't find it, click the Raise Hidden, it'll bring it up front. Okay, so spring constant K250, click OK. That'll be our set 1. Go here and click add again to do set 2. It'll ask you what element type, just click OK. Notice that auto incremented the real constant set number to 2 now. Now we need to specify K2, which is 320. So type 320 in for the K value. Click OK. So there's set 2. So we got to add 2 more. So click add, OK again. Now it's on a real constant at 3. The value there is 520. So type 520 in for the K value. Click OK. 1, 2, 3, and then click add one more time. OK. And let's specify K4, which is 200. And then click OK. So you should have 4 sets. If you need to go back and change any of these, you can click on the corresponding set. You can go to Edit, OK, and it'll bring back up the window here. Notice the ones we left blank, it put the default value in a 0 for that. All right, so when we zero out CV1, CV2, the system has no dampening in it. It's really a spring system. All right, so let me pause. Any issues up to now? Anybody has? All right, good. So go ahead and close out of the real constants. What we're going to do now is we're going to create the nodes that represent the rigid plates. The way that we do that is go to Modeling, Create Nodes in Active CS, which stands for an Active Coordinate System. And then we're going to specify node 1 at 0, 0, 0. And then you'll notice we'll do node 2 at 1,000, 0, 0. So it's 1,000 meters in the x direction from node 1. But okay, let's start with first node here. So come out of real constants, go down to modeling, create nodes, and then you'll see an active CS, which stands for an active coordinate system. Click on that. You'll get this prompt. It wants you to specify the node number, so put 1 in for the node number. And then it wants you to specify the location in the coordinate system. So put 0, 0, 0. And then it also is asking for the rotation angles, theta xy, theta yz, and theta zx. We're going to leave those blank. We don't need to use those for this element. So if we click OK, which go ahead and do this, click OK, it'll close the window out. And it added the node at the origin here. You can't quite see it because it's covered by the coordinate system. All right, so take my word, it's there. Let's go ahead and create the next one. So go back on the menu here on the left, modeling, create, nodes, and active CS. Click that again. It'll bring this prompt up again. Let's change the node number to 2 now. And then let's specify the location to be 1000 in the X, 0 in the Y, 0 in the Z. And then on this one, let's click apply instead of OK. And if we click apply, it'll keep this prompt open since we need to make 3 more nodes. Click apply. Notice it didn't close this window out, so now we can do the next one. If we click OK, it's OK. We just have to go back on the menu and re-click an active coordinate system. So whenever you see an apply, it's going to keep the prompt open. Next, we got to do node 3. I'm going to show you a shortcut here. Instead of having to keep incrementing these manually, you can type next in for the node number. It'll auto increment for you. And then all you have to do is specify the new coordinate of the next node, which will be 2000, 0, 0. All right, click apply to keep the prompt open. So there you go. You should see some stuff change in the background. So there's node 3. We need 5 of them, so we got to go 2 more. So change 2000 to 3000. Click apply. Here's node 4. And then change the 3000 to 4000. On this last one, click OK to close the prompt. All right, any issues on creating nodes?
It's just displaying node.
Okay, yeah, so one thing you may have to do is click on fit the view right here. Look on the right hand side, these are all our predefined views and view keys. That works. Yeah, so if you get zoomed in too far, click fit the view. I want to show you some other keys to change a view. If you hold control on your keyboard, the left control, and you press down with the right mouse button, you can rotate the model. If you're still holding control and you press your left mouse button, you can pan. And if you let go of control and you scroll with the third mouse button, you can zoom in and out. Those are mainly the mouse keys I use. So rotate by holding control on the right mouse button. Control on the left mouse button pans. And then third mouse button zooms in and out. So once you've kind of messed with those controls a little bit, if you go on the right hand side here, the first couple of icons here are the predefined views. You can click on those. I'll get you reoriented. To get back to the view that we started off with, it would be the front view, which is the third one down. Click on that, and then go down and click on fit view, which is the magnifying glass with the cube. It should get you back in the view we were at the beginning there. Can anyone not see their nodes or anything? Everybody see nodes? Ah, good. You guys are doing awesome. Okay, so we got our nodes in there. Those represent our rigid plates. Our next task is going to be to create the elements that connect the nodes together. And then we'll put the boundary conditions on, which will be a fixed condition here, and then our forces, and then we'll solve it. So let's work on the elements that connect the nodes now. So if you look at the how-to, we're going to go to modeling, create element. We're going to set the element attributes first. And let's start with K1. So we'll set the element attribute to be a 1. And then we'll go to element, auto numbering through nodes. We'll select nodes 1 and 2, hit apply. We'll do that twice because there's 2 K1s. If I look at my system here, here's a K1 here, there's a K1 here, so I need to do that twice. And then we'll do between nodes 4 and 5 too, because there's a K1 right here. And then we'll go on to K2, K3, K4. Okay, so let's set the attributes first. So modeling, create element attributes. Let's do that. So modeling, create elements. We've got element attributes. Come down the real constant set number and click this drop down menu here, and you'll see 4 values there that represent our 4K values. Let's set it at 1 to start out with. So we're going to draw element K1 first. Click OK. And then go down to auto numbering through nodes. You'll get this window to show up. If you ever get a window to show up, you're not sure what to do, if you read in the lower left-hand corner, it does tell you what it wants you to do. So it says pick or enter nodes defining the elements. So let's start with our K1. We have a node here at the origin. So click that, and you'll see a yellow box outlining that node. If you select the wrong node, there's an unpick option here. You just click unpick and go back and click the yellow box. It'll unpick it. But we want to have node 1 selected, and then we also want to have node 2 selected. All right. And then we're going to keep this prompt open, so I'm going to click apply instead of OK. And you should see it draws a cyan line that represents the element there. And then we want to click node 1 again and node 2 again. And this is going to create our second element right here. Right, we got 2 elements between nodes 1 and node 2. So click apply again. It's going to overlap with that previous element, so you're not going to see much change in your figure. And then we need to click between node 4 and node 5 to make this last element K1 here. So go click 4, click 5, and then click OK. And that'll close the prompt there. All right, so now everybody go up to list elements and click on nodes plus attributes. And if you do that, you'll get a listing of the elements we just created. So we created 3 elements, element 1, 2, and 3. You see the real constant number here is set at 1. And then you also see on the last 2 columns the nodes is between. So element 1 is between nodes 1 and 2. Element 2 is between 1 and 2. And then element 3 is between 4 and 5. If you create an extra element, what you can do is instead of going to create, you go down to delete elements. You'll get a similar prompt. You can either manually pick it by clicking on it, or you can type in the element number in this prompt here and then hit OK. But since we made all the correct elements, we don't need to delete any. There is that option to delete elements below create. Yep.
Back to the list for the elements node.
Sure. you see it? It's element 1, 2, and 3. So the order that you make these elements really doesn't matter. It just matters that you have 3 elements right now, and they're between the correct node numbers. You need me to come back there? You got it.
You didn't work there. You didn't work though. He also literally said we're doing it in 1 week before we're doing it in the next year. I know. Because the projects we're doing currently. Obviously, right, Sam? Is that what you created? Yeah, like that's all.
All right, so again, the element number doesn't matter. Just matters that you have 3 elements between the correct nodes, right? So if you made these out of order, say made this one first, this would be element 1, this would be element 2, and this would be element 3. You get the same result in the end. Okay, so let's work on K2. It's between nodes 2 and 3. It doesn't show up anywhere else, so we just have 1 element to make. Before we go and create that element, we need to set the element attributes. Right, so we need to go element attributes and set it to 2, and then go ahead and create the element. So modeling, create elements, click on element attributes first. Come down to real constant set number. Change that 1 to a 2, the drop-down menu here. Click OK. And then now go to auto numbering through nodes. Click node 2 and 3, and click OK to close the prompt there. And if you go to list, elements, nodes plus attributes, you should see we have now a 4th element. It has real constant set 2, and then it's between nodes 2 and 3. All right, let me show you one other thing before we make the last 2 elements. Zoom in and out on your screen, like this with the 3rd mouse button. You'll notice the elements look like they disappeared. The reason why they disappeared is because the plot refreshed when you zoomed in and out. And if you look up in the upper left-hand corner, the plot that was refreshed was the nodes plots. So the elements weren't generating the nodes plots, it's only plotting the nodes. If you go up the plot, so go ahead and do this, go to plot. You can come down to elements, And you'll see that we got the elements back, but now we don't have the nodes. You'll notice in the upper left-hand corner, it's elements plot labeled up there. So if we go up to plots and we go down to multi-plots, which is the second one from the bottom there, we have elements and nodes plotted here. So you should see a little white dot each of the nodes. So that's good. But now we lost our labeling. So we don't have our node numbers on there anymore. So let's go ahead and turn on node numbers, and let's also turn on the element numbers for each of these elements. If you go to plot controls and you go down to numbering, third one down there, click on that. And then look down this listing until you see node numbers, and you'll see an off ratio there. That's what it's called. Click on that and it'll turn on. And then below that you'll see element/attribute numbering. Change node numbering to element numbering. Right. And then if you look a little bit further down, you'll see numbering shown with colors and numbers. So it's also going to color the elements a different color if they're a different element number. Go ahead and click OK. And there we go. So the node 1 is covered up by the origin, the Y direction arrow there. But you can see node 2, node 3, node 4, node 5, and then the numbers between those represents the element numbers. So this is element 4 between nodes 2 and node 3. This is element 3 between 4 and 5. And then between nodes 1 and 2, we actually have 2 elements. We have 2 numbers overlapping. So that's why it kind of looks like a jumbled up 2 there, because it's a 1 and a 2. All right. So let's go ahead and create the last 2 elements. K3 is next. K3 shows up between nodes 1 and node 2. Let's first start by defining our attributes, and then we'll create the nodes. So again, element attributes. So element, create elements, element attributes. Let's change the real constant set number to 3. Click OK. And then go down to auto numbering through nodes and select node 1 and node 2 and click OK. So now that element number is looking even more jumbled, right? Because it's got 1, 2, and 5 now transposed on top of each other, or superimposed. All right, so that's K3. Let's do K4, which is between 3 and 4 and 4 and 5 here. So again, first change your element attributes to 4. So real constant set 4, click OK. And then go to auto numbering through nodes. Click on 3 to 4. Apply to keep the prompt open. And then 4 to 5, and click OK to close the prompt. All right, if you go to list, elements, nodes plus attributes, you should have 7 elements. First 3 have elements attribute 1. Element 4 is element attribute, real constant 2. Element 5 is real constant 3, and then the last 2 have real constant 4. Yeah. Make sure you're on multi-plot. Go to plot. Make sure you're on multi-plots. So it's plotting both the nodes and elements. that fix it? All right. Any other issues? Anybody have? Okay, so now we got to put some boundary conditions on here. So the first one we're going to start with is this fixed boundary condition on the right-hand side. Basically, I'm going to click on the node that represents this rigid plate. I'm going to tell it that it cannot displace in the X, Y, or Z direction. Basically fix it. And then what I'm going to do is I'm going to click on the remaining 4 nodes and tell it that it can't move in the Y or the Z direction. It can only move in the X direction. And then we'll put our forces on. All right, so let's start with that node on the far right. So if you go to loads, define loads, structural displacement, we're going to select node 5. And we're going to select all degrees of freedom and specify a value of 0. So let's come out of modeling. Let's go down to loads. Define loads. Apply structural displacement. Then click on nodes. Get this familiar window again. If you read in the lower left-hand corner, it says pick or enter nodes for displacement constraint. So we're going to pick node 5. Click OK. And then you'll get this list, scroll on it, of all the degrees of freedom for that node. So you'll see UX, UI, UZ. Those are translations in the X, Y, Z. And then you also see velocity X, velocity Y, and velocity Z. So in our case, we're doing a static structural problem. Some forces equal 0. So the velocity is always going to be 0. So we can kind of neglect the velocity terms. So we're only interested in the U terms here, UX, UI, UZ. And we want to make all 3 of these 0. So an easy way to do that is just click all degrees of freedom. And then we want the displacement value to be 0 meters. Put a 0 in there. And then click OK. And you should see a little symbol support show up on node 5. And if you hold Control on your keyboard and use the right mouse button and rotate, you'll see that the support symbol is in all 3 Cartesian directions. It's got like a support in the X, a support in the Y, and a support in the Z. All right, I'm going to go back to front view, fit view, bring it back. So we read in the help menu that each node has 3 degrees of freedom. We just constrained the 3 degrees of freedom on node 5, but on node 4, 3, 2, and 1, we don't want it to move in the Y or the Z direction. So we don't want to move in the vertical direction or out of the plane direction, but we do want it to move in the X. So we apply forces to these nodes. We want it to move in the X direction only. So what we want to do is we want to click on these 4 remaining nodes and only specify the U, Y, and the UZ directions for degrees of freedom to be 0, not the UX. So click on displacements on nodes and click the 4 remaining nodes. Click OK. And then click on all degrees of freedom and turn it off. And then we only want to click on UY and UZ. Right? We want to leave UX unselected. That means that degree of freedom is still free to move. But UI and UZ are always going to be 0 for those nodes. When the displacement value is 0, and then click OK. You should see that the support is only in the Y direction, the Z direction. There's no support in the X direction. That's what we want. Yeah.
How can you go back through and like edit a node and just like see what the constraints are?
So do you want to see the constraints or delete one?
For the fifth one, I can't remember. I didn't know that you could like click on it.
Yeah. So if you go to list, you can go down to loads. And you go degree of freedom constraints, and then on all nodes. Then I'll list the node numbers, the associated degree of freedom, and then the real value is the value specified in there for the displacement. So you'll see node 5 right here. It has all three UX, UI, UZ, and its value is 0. And then you'll see node 1 only has UI, UZ, node 2 only has YZ, 3 YZ, 4 YZ. If you want to delete one of these degrees of freedom, say you put the X's on nodes 1 through 4, you can come out of apply and go down to delete, structural displacements on nodes. It says pick or enter nodes for degree of freedom constraint deletion. You would select those 4 nodes. Click OK. And then it'll ask you which degree of freedom you want to delete. You can click UX, for example, click OK, and it'll delete that degree of freedom. Okay, so we got our model held in place now. We got a rigid wall over here on 5. Let's apply the forces now. If you look at the figure, we have 3 forces. F1 is 10,000 kilonewtons in the positive x direction. Force 2 is a negative 2 kilonewtons in the negative x direction. And then force 4 is 5 kilonewtons. And then we don't have a force on node 3 or node 5. So let's start with F1. It has units of a kilonewton, so we need to convert that to newtons by multiplying times 1,000. Right, so this is going to be 1,000 or 10,000 newtons for F1. The way that we apply the force is we go to loads, define loads, apply structural force/moment on nodes. You get this familiar prompt. You read in the lower left-hand corner, it says pick or enter nodes for force/moment loading. You're going to pick node 1. Click OK. It's going to ask you what direction do you want the force and moments. So we want this in the x direction, so select FX. And then it's going to ask you for the force/moment value. You're going to type in a positive 10,000 in for that. So 10 and 3 zeros. And then click OK once you do that. You should see a red vector that represents the force show up there. All right, so that's the first force. Let's go to the second force, F2. It's going to be a negative 2,000. So click on force/moment on nodes again. Now click node 2. Click OK. Should be in the FX direction again, but the value is going to be a negative 2,000 because it's in the negative x direction. Click OK. You should see a red vector point in the negative x direction now. And then let's do the final force F4, which will be 5,000 in the positive x direction on node 4. So force/moment on nodes, click on node 4, click OK, and then specify the value to be 5,000 in the FX, hit OK again. You should see a red vector show up that represents that force. If you zoom in and out, it'll rescale those vectors depending on the magnitude of the force. So notice the vector at node 2 is smaller than the magnitude of vector force 2 is smaller than that of magnitude at force 4. This one was 5,000, this one's 2,000. And then the force at magnitude of force 1 is the largest, because it's the largest force. All right, so we're ready to solve this thing now. So let's come out of preprocessor. So you can hit on the minuses, come back out of preprocessor. We're now down to the next major menu item, which is the solution. And first we need to define what analysis type we want to conduct. So click on analysis type, click on new analysis. And here's all the possible analyses we can run, right? So static, structural. So static is sum of forces equals 0. That's what we're doing here. Modal would be natural frequencies. Harmonic would be the forces are applied as sine waves. Transient would be it's a function of time. Spectrum would be like a random phase on the force. Eigenbuckling would determine the buckling modes. And substructuring would it be if this was like a substructure of some larger structure. All right, so we're going to keep it on static structural. Click OK. Come out of analysis setting, analysis type, and come down to solve. You'll see current LS, which stands for current load step. Click on that. You get two windows that show up. The one on top here says begin solution of current load step. Review the summary information in the lister window entitled /status command, which is this one back here. Then press OK to start the solution. So it's, if you look back on this status command window, it's actually a three-dimensional simulation with degrees of freedom in UX, UI, UZ, but we constrain the UX, UI, and UZ at each node. So it's effectively a one-dimensional result, but it is solving the full 3D stiffness matrix. All right, and then the analysis type is steady state, static steady state. So sum of forces equals 0. So go ahead and click OK. If we did everything correct, you should get solutions done. Right? If you click OK and you don't get solutions done, you need to check back on the output window and see what error it presented there. Usually it's like an insufficiently constrained model, which means you left off some boundary conditions, or you have an element that's not correct. All right, so hit close on that. Come back out of solution, and then come down to general post-processing. And let's go to list results, nodal solution, and then click on degree of freedom solution, X component of displacement. So now we're going to look at our results. We're going to start by looking at the displacement of each of the nodes. So I'm going to list the displacement of each nodes. Click OK. We get a listing. Here's our 5 nodes. The UX is the displacement value in meters of those nodes. And then below that is the max absolute value from that listing. So it's saying node 1 moved 103.69 meters in the positive x direction. So the sign on this value matters, right? So when it's positive, it's moving in the positive x direction. It's saying node 2 moved 94 meters in the x direction. Node 3 moved 69 meters in the x direction. Node 4 moved 29 meters in the x direction. And then node 5 moved 0 meters. The reason why it moved 0 is because we constrained this displacement to be 0. So kind of what you thought, you got the largest force out over here on node 1 pushing in the positive x, so all the nodes kind of move positive x as the springs compress. So that's the displacement. If you go below nodal solution, you can get the reaction solution. Get this list reaction solution. Just keep it as the default all items, click OK. And It'll list the nodes out that have degree of freedom constraints on. So we constrain nodes 1 through 4 in the UY and UZ direction, but there was no force applied in the UY, UZ, so those are the zero reaction forces. At node 5, we constrained it in the X direction, so we see a reaction of 13,000 newtons. If we look at the problem, we can do simple statics to confirm that value is correct. So we have 10,000 and a positive X at F1. We have negative 2,000 at F2, so that's 8,000 if we add those together. And then we have another 5,000 and a positive X, so 8 plus 5 is 13,000. So we got 13,000 in the positive X direction. The reaction force will be equal and opposite to that. So we see from ANSYS it's a negative 13,000, which means reacting in the negative X direction to equal out that positive applied force of 13,000. So that's correct. That's the same as what we get from statics. If we want to visualize the displacement, the last thing we can do is we can go out of list results and we can go up to plot results, and we can do a vector plot. And then click predefined. And then let's look at a vector plot of degree of freedom solution, which is just the default selection. Click OK. And we get a vector plot of the displacement of each of the nodes. So these vectors represent magnitude and direction of the nodal displacements. Colors represent the magnitude and the direction. The vectors pointing the direction of it. It's only in the X direction. You see node 1 is the largest. It's got 103 value. Node 2 was at 94. So it's still within the red region, so its vector is still red. Node 3 is 40 some. 60 green. All right. And those commands to get those are listed in the how-to here. All right, so that concludes the lab for the day. Congratulations on your first simulation in ANSYS. Does anybody have any questions before we break?
Yeah. Can you just hit save now? Save it.
Oh yeah, good question. So if you're going to save this to your thumb drive or OneDrive or Google Drive, click Save on Analysis right here. Go ahead and exit out of ANSYS. It'll prompt you again to save it again. Just click OK. And then what you want to do is you want to go to Explorer, find your working directory. So go to the Explorer down here, Documents, Section 2, Assignment 1. And you'll see a file here called DB. That's the file you want to save to your thumb drive or OneDrive. You just need to save this one file right there. 128K. It's not very big. All right. Yeah. Any other questions? Anybody have?